Now we are moving on to water flow. Water flow dictates the carrying capacity of the tank. So the faster we can export the waste products from the fish, the more fish we can keep in the culture tank. The carrying capacity is first limited by oxygen, then by waste accumulation in the tank. So our first limitation is not by removing that waste, it's actually providing enough oxygen for the fish that are being cultured. But then after that, it's waste accumulation. Water exchange in the culture tank must be adequate to export the waste products fast enough to keep water quality parameters within ideal standards for the species being cultured. Now we can calculate the actual required flow by analysis of the water flow, which we will call Q, and the efficiency of the waste removal, which we will call E, at each step of the process in the recirculating aquaculture system. So in solids removal, we have to look at the water flow through the filtration, through, if we're going to do any kind of sedimentation, removal of finer solids. If we're going to have to do any kind of chemical filtration, and whether that has a different required flow rate than the entire flow through the culture tank. We need to look at CO2 removal and degassing that. Does the degassing apparatus have a different required flow rate than our total flow rate? Maybe a higher head pressure, maybe we need a separate pump. So we need to look at that. And then for the ammonia removal, for our biofiltration, we have to look at the specific flow rate required to flow through that media to actually process the ammonia and the nitrite. So we'll be analyzing the flow rate through that piece of equipment. So we're going to do a quick sample question or problem here. We have 4,000 gallons in a culture tank being fed 10 pounds of food per day. And again, you see the metrics here if you want to do metrics. The steps are calculate the TAN, and then size the biofilter, then obtain the required flow rate for processing ammonia. So that's in part of sizing the biofilter. Size mechanical filtration. So we need to size the mechanical filtration and look at the required flow rate through that piece of equipment. Most pieces of equipment like a swirl separator or a radial flow separator will have a specific residence time that the water needs to sit in there for the particles to slow down enough to fall out of suspension. Something like a rotating drum screen filter will have a maximum flow rate that can flow through that piece of equipment. So we need to look at those standards for the equipments we're using. Size oxygen equipment. So we need to size the oxygen equipment, run the calculations, which we'll do here shortly, and then obtain the required flow rate for dissolving that gas into the vessels like a species cone or a low head oxygenation device, and then delivering it to the culture tank. So we have to size the oxygen first, obtain the required flow rate for the piece of equipment we're using, and then deliver that to the culture tank. We have to size our heat pumps to obtain a flow rate for that. So a heat pump is what you use to either cool or heat the water in a recirculating aquaculture system. Think of it like an air conditioning, central air and heat for your house. Very similar, but the coils are submerged and the water flows by those coils and absorbs the energy. We need to size the water pumps for the total flow that we just mentioned in the slides before. Large systems often use multiple pumps to supply the needed flow to individual components because some of these components are going to have different flow requirements. So let's say a heat pump, it may only take, let's just throw a number out there, 10 gallons per minute, where the entire flow may be 150 gallons per minute. Well, we could tee off of that entire flow and send 10 gallons a minute through that piece of equipment, or we could actually pull a separate pump and specify it specifically for that 10 gallons per minute. And we'll get into a lot more of that when we're actually sizing all of the equipment in a later session. So here's a shortcut for water flow, and that is you can turn the tank volume over once every 30 minutes for fry or fish that are very small, fragile, and require extremely good water quality, and about 1 time an hour for adults, and for biofiltration, mechanical filtration components. So about 1 time an hour for your culture tank. That is just an average that if you need a quick number and you're just sizing on the fly and you don't have time to run the long calculations, these are very often used and numbers that work. So we size a heat pump and oxygen requirements separately. Talk a little bit about oxygenation devices. Now, oxygenation devices allow for higher densities, so densities up to and beyond 1 pound per gallon, which is 120 kilograms per cubic meter. And that depends on species and experience. So, real easy way to think about this is that in the air that we're breathing every day, we have just about 20% of oxygen in the air. If we're using pure oxygen, we can get 90 to 99% oxygen injected into that water. So right there you can see that's roughly 5 times the oxygen that we can get out of atmospheric air, which leads to us being able to keep higher densities. So it's favored for better optimization of controlled environment space. Let's say we have a 1 acre building and we fill it up with fish tanks and equipment. Every square foot is used in that building very efficiently. Well, with oxygen, we can fit twice as many animals in the same space. So it makes sense if you're paying the money for that large controlled environmental space that costs a lot to control, it makes sense to grow twice as many animals in that same space. And again, we size the filtration according to those fish, how many we're carrying and the carrying capacity and the feed that's related to that. Again, the oxygen is delivered via bottled oxygen or oxygen concentrator, oxygen generator, which means if it's delivered by a truck, usually you have an on-site tank that you will have the oxygen supply company fill up, and you run your main lines off of that into your facility. You sign a contract with the oxygen supply company and you have them on a fill contract so that you never run out. An oxygen generator is actually a device that generates oxygen on site. Typically, in my experience, 92 to 96% oxygen. You'll get a higher percentage of oxygen from an oxygen bottling plant using liquid oxygen, which you'll hear me mention as LOX or LOX. That's liquid oxygen. It's the term for that. So anyways, moving on, we inject that through a pressurized device such as a Spiess cone, which we'll talk about later, a low head oxygenator, or through a fine pore air stone, which is probably the least efficient method. But we want to inject this and try to get as much of that oxygen to dissolve into the water before the bubbles reach the surface. So in a fine pore air stone, again, bubbles will slowly rise and reach the surface. Through a Spiess cone or low head oxygenator, we'll actually completely dissolve that oxygen. Well, through the Spiess cone, a low head oxygenator is a little less efficient, but we'll talk about these when we talk about equipment. Aeration equipment is favored for lower density production, so we can go up to a ½ pound per gallon of fish per water. That's 60 kilograms per cubic meter, and that's using properly sized aeration device, which we will learn how to size blowers, air pumps, linear piston compressors, all that in the equipment section. Here we're going to learn how to actually come up with the needed oxygen or air requirements, and then we'll relate that to the equipment when we do the equipment sizing. So again, right here, diaphragm air pumps, linear piston air pumps, or regenerative air blowers are commonly used to do this. Now, we need to understand mass transport. Okay, we're getting into some mass balance equations, so a little bit more math here. And the biggest thing that I can suggest is for all my non-math people, write out the equations longhand, and again, just switch in your numbers for the numbers that I've provided here in examples. It makes these go a lot easier than starting from this equation, flow times concentration equals mass per time. If you start with that equation every time, it can get pretty confusing. But follow the steps that we're going to go through here, and it'll make it a lot easier. So, right here is one of the first formulas, and again, this is the formula for mass transport, and that is flow times concentration equals mass per time. So we'll get into an example, and we're going to say we have 100 gallons per minute. That's going to be our flow, and then the concentration, which is concentration of oxygen, is going to be 10 milligrams per liter. So that's how much oxygen is in the water. 100 gallons per minute, the flow. 10 milligrams per liter, how much oxygen is in that water, okay? That's pretty easy. Well, when we multiply these two together, we get something that does not compute. We get 1,000 gallons times milligram over minutes times liter. Now, there's nothing for these to actually cancel out, and that's not a true value. That doesn't tell us anything. So we need to rearrange these formulas and extrapolate this to give us the information that we need. So from that original formula, we're going to go ahead and do a little bit of unit conversions here. We've still got 100 gallons per minute, but now we're going to add in 3.785 liters per 1 gallon. Because there's 3.785 liters in 1 gallon, and we eventually want the gallons to cancel out. So times 10 milligrams per liter equals 3,785 milligrams per minute. So now we're getting somewhere. We're extrapolating these out, and we're getting to a point where we're actually going to be able to cancel out some of these factors and get a real-world number that tells us something. As you can see here, we still have milligrams beside each other. These are not able to cancel out, so we have to go another step further and bring milligrams over to this side. So once we do that, we've got 3,785 milligrams per minute times 60 minutes in 1 hour times 24 hours in 1 day times 1 gram in 1,000 milligrams times 1 pound, which is 453.6 grams. Okay, so there we've laid it all out. We've extrapolated that as much as we can to get common factors that will cancel out. And you see milligrams cancels with milligrams. We see minutes cancels with minutes. We see hours cancels with hours. We see, what are we left here? Milligrams with milligrams, grams with grams. And what we're left with, once you do this multiplication, so you literally multiply 3,785 times 60 times 24 times 1 over 1,000 times 1 over 453.6. That's the actual math. And you're going to get 12.02 pounds per day. 12.02 pounds of oxygen per day is what you actually need. So we've got 100 gallons at 10 milligrams per liter equals 12.02 pounds of oxygen per day, which is 5.5 kilograms per day. This is something we can work with. Okay, we know how many pounds of oxygen we have going into the system every day. We can calculate how many pounds of oxygen the fish are going to consume by eating that food. So that tells us how much the fish need. Then it will tell us how much oxygen is leaving the tank. This is exactly what we need to design the oxygenation or aeration system. So again, don't get confused with that equation. We extrapolated it out as far as possible so that we could cancel and come up with a working number. For steady state mass balance, the ins must equal the outs. So after we add fish to this equation, we need to calculate their oxygen consumption to maintain the desired milligrams per liter of oxygen concentration in that water volume. So to maintain the fish's water quality standards, what it needs to live a healthy life. Fish consume oxygen in proportion to the amount of food that they eat. Oxygen consumption is 25% of the feed weight in single pass systems. Okay, so flow through systems, 25% of the feed weight. It's 40 to 50% of the weight in a partial reuse system. So think 50, 60% reuse, probably closer to 50% reuse. And then in a fully recycled system, it's 50 to 100% of the feed weight. So if you want to be safe, you go with 100% of the feed weight when you're using a recycle system, because that's our highest factor. Using an oxygen generator, it will only produce what you need because you have that hooked to a probe that actually tells you what the oxygen level is in the water. So you won't be using more than you need. You may have to actually size that piece of equipment slightly smaller, but you'll look at that when you're choosing a piece of equipment. How close is the next size up? Compared to how much you're predicting you may need. So in this example, we're actually going to use 25% oxygen consumption per pound of food, or per the weight of the food for the example. So if we have 40 pounds of feed per day, that's 18 kilograms, and that means we have 10 pounds of oxygen consumed per day. So it's 25%. 40 times 25%, we get 10 pounds. Pretty easy calculation. We move on here. 12 pounds a day, which is 5.4 kilograms, going into the fish culture tank, and the fish are consuming 10 pounds a day, which is 4.5 kilograms. And then we have the water leaving the culture tank, okay? And that's represented by the following equation. 100 gallons per minute at X milligrams per liter. So we don't know the milligrams per liter of oxygen leaving the tank. We know the flow rate going in is 100 gallons per minute. So we want to solve for X. 12 pounds per day equals 10 pounds per day plus 100 gallons a minute at X milligrams per liter. Okay? That's pretty easy. Let's move to the next step. 12 pounds per day minus 10 pounds per day equals 100 gallons per minute times 3.785 liters per gallon times 1,440 minutes per day times X milligrams per liter. So again, we're trying to get this into terms where we can cancel out some of these common gallons, liters, etc., so that we can come up with a final answer here. Once we move on from this equation, 12 pounds minus 10 pounds a day, 2 pounds a day, then we do our multiplication here and we get our answer. It's 2 pounds per day, so 2 pounds divided by day times 4,500. So we move on to the next step of the equation. And that's here. We've got 2 pounds per day times 453,600 milligrams in 1 pound. That's just a fact. We know by looking up how many milligrams in a pound, that's the answer. Now we go ahead and do this math and we divide this by the next section. And unfortunately, it's such a long equation, I can't get it all the way across there in one line, or it gets really small on the screen. So we do this area of the multiplication, and then we divide that by 100 gallons per minute times 3.785 liters per gallon times 1,440 minutes per day. And that's going to give us how many milligrams per liter of oxygen are leaving the tank. Right here we do that math and we come out with 1.66 milligrams per liter coming out of the culture tank. And that's low. That means by the time the oxygen's in, the fish have used what they need and the water's leaving, it's extremely low. In fact, that's too low. So the water entering the tank is 10 milligrams per liter. The water exiting the tank is 1.66 milligrams per liter. If we want to maintain a minimum of 6 milligrams per liter, say we're doing trout or tilapia, and we have figured that for best culture practices, by looking into that specific species, we want to maintain 6 milligrams per liter. Well, then we set that as our low point. We want it leaving the tank at 6, not at 1.66. So we go ahead and we say 6 milligrams per liter minus 1.66 equals 4.34 milligrams per liter. That's the deficit there. We add that to our incoming water concentration. It's coming in at 10 milligrams per liter. So if we add the 4.34 milligrams per liter that we have calculated, we get 14.34 milligrams per liter. That is what we want to inject into the tank. If our injected water has an oxygen saturation of 14.34 milligrams per liter, then after the feeding and all of the processes in the culture tank, the water will leave at 6 milligrams per liter, which is completely acceptable because we went ahead and looked up the species we're culturing and we made sure of that. If this was 8 milligrams per liter, we could calculate it for that. If it was 3 milligrams per liter, we could do that calculation. So it's species dependent, but the math will give you the answer no matter what you go through. I hope you got that. Do several of those equations so that you get familiar with it. Practice makes perfect. So we're going to do another example. And in this example, we're saying, what if we have a required dissolved oxygen, we'll call that RDO, of 1.13 kilograms, and that's what's consumed per day. 2.5 pounds of oxygen consumed per day. Well, what if we know that? If we've calculated that's what the fish are going to consume from their fish feed. Okay, well here's an equation that's going to help us out here. Q flow equals RDO, the required dissolved oxygen that we know from the feed and the species that we're culturing. So RDO times 1 over the DO inlet minus the DO effluent, the outlet. So Q flow equals required dissolved oxygen times 1 over our inlet oxygen level minus the outlet oxygen level. And we'll do a quick example here. We've got 1.13 kilograms of dissolved oxygen per day. That's what we've calculated that we need. We multiply that by there's 10 to the 6 milligrams per kilogram, okay? So 10 million milligrams per kilogram. We multiply that times liter over 14.34 minus 6 milligrams per liter. So we just used the same criteria that we did off of the last equation, 14.34 minus 6, and then we multiply that by, there's 1,440 minutes in a day, okay? And this is all, again, so that we can get things to cancel and come up with a final answer. We do the math there, and we end up with 94 liters per minute, or 24.8 gallons per minute. So that's the required flow rate that we need to have to actually sustain the dissolved oxygen that we want. Okay? And now this is directly related to the equation we just did during the last slides. And if you'll notice, this is roughly 1/4 the flow from the previous equation for 10 pounds of oxygen consumed per day. So it's 1/4 the flow because we have 1/4 the oxygen consumption. We have 2.5 pounds. And you can see how these equations actually work together. If you do a few, do them with both equations, and you'll see you can work from either way. If you know the dissolved oxygen requirement, you can use this to calculate the flow rate. If you know the flow rate and the oxygen, you can use that to calculate the dissolved oxygen requirements. So both of these work very good, and they're formulas that you need to know to calculate needed flow rates. Okay, and we'll do another example. So what if we have a required DO, an RDO, of 10 pounds of oxygen consumed per day? Again, Q flow equals RDO times 1 over the DO inlet minus the DO outlet concentration. 45 kilograms of DO per day times 10 to the 6th milligram per kilogram times 1 over our DO inlet minus the outlet concentration times day over 1440 minutes. And that gives us with 3,747 liters per minute or 989 gallons per minute. Dissolved CO2 is fairly easy to calculate because that is 1.375 times the dissolved oxygen concentration. So we calculate dissolved CO2 from the last exercise. We can see that we have 40 pounds or 18 kilograms of feed per day. We have 10 pounds of oxygen consumed per day. Well, we take that 10 pounds of oxygen times 1.375, a constant factor, and we get 13.75 pounds of CO2 produced per day. We use that to calculate whether or not we need to actually off-gas and degas CO2, and we'll talk about that when we're sizing equipment and we go through degassing equipment. So here is a nice table when you print this out that you can actually use to calculate what's the highest dissolved oxygen concentration you can achieve using ambient air. So if we're using an air compressor or an air blower, something like that to give air to our fish, what's the highest concentration that we can achieve? Well, it has to do directly related with the water temperature. Okay, so what you do is you take a ruler to this, and this is water temperature in centigrade, and you go ahead and say we're at 20 centigrade. So you put your ruler on there. And then you go down to what percent saturation you actually want to keep the water. Say your species is fine with keeping the water at 80% saturation. Then you would go put your ruler on 20, put it to 80, and the end of the ruler will go down and tell you how many part per million of oxygen you've actually got in the water at that temperature and at that saturation point. So if you want to see maximum saturation points at any given temperature, you simply go to 100. So you would put your ruler on 20, you would go through the 100 mark, and it would come down and it would show you at 20 degrees centigrade, 100% saturated water is going to be, and it will, I can't tell you right now without the ruler, but down here in this area, and it will give you the exact part per million achievable using ambient air. And that's very predictable and dependable because we know it depends on the water temperature. Here's another table showing us the same thing, but just in a little bit different way. You can just see on the graph, here's the milligrams per liter of oxygen, the solubility here, and here's the temperature. So as temperature, we're at 20 degrees, we go up and we can see what the max solubility of oxygen, the saturation point is. So both of these you can use for estimating and predicting. So to calculate oxygen requirements, first we need to calculate the feed rate, and we already learned how to do that. Next, we want to determine the flow rate, which we actually just determined how to do. Then we can calculate the oxygen requirement. If using oxygen, we size the supply tank or generator using how many pounds of oxygen we need per day, using that calculated number. If we're using ambient air, we can also use the calculated oxygen pounds per day or per hour to calculate the needed air volume in cubic feet per minute, or liters per minute for our metrics. For aeration sizing, establishing the volume of air required in CFM takes the following steps. So first, we need to estimate the maximum feeding rate and stocking density at the time of harvest. So this is really important. We always want to size on the maximum stocking density. You can always deliver air somewhere else, deliver it to the same culture tank, or bleed it off if you don't have that many fish to begin with. But you can't increase the size of your aeration equipment when the time comes that your fish have grown to that size. So we need to account for maximum size right off the bat. Then we can calculate the oxygen requirements in pounds of oxygen per hour, and that's biomass times oxygen consumption, and we've already done that. We look up the standard, the SOTE, which is the standard oxygen transfer efficiency for the air diffuser that we're looking at using. So it tells us the efficiency of how many pounds of oxygen we're injecting versus how many pounds are actually getting dissolved into the water column. That's very important because not all diffusers are the same. If you have a very large bubble, you'll get a lower standard oxygen transfer efficiency than if you have a smaller bubble. Now we want to divide that calculated oxygen pounds per hour by the SOTE of the air stone and multiply it by the given CFM of the air stone to get the volume of the air needed. So we can do that by calculating the oxygen requirements in oxygens per pounds per hour, which is biomass times the oxygen consumption of that biomass. We look up the SOTE, which is the standard oxygen transfer efficiency rating for the specific air stone that we're choosing to use, and then we divide the calculated oxygen in pounds per hour by the SOTE of the air stone and multiply it by the given CFM of the air stone to get the volume of air needed in CFM. Now, not all air stones are created equal, so if you have a cheaper, less uniform bubble, you're going to get a much lower SOTE than if you have a higher quality air stone that's delivering a uniform bubble throughout the surface of the stone. So this is really one of the cases where you get what you pay for. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.